Periodic trends. This is the stuff we need to understand the lab we did last week. So there are trends in the periodic table. One of them is atomic size, and you graphed that, and you saw it was this really weird graph. But there's a trend. Atomic size can be defined in many ways. We're just going to go with kind of a generic definition. The distance between the outermost electrons and the nucleus. Okay, so you got electrons in increasingly big, increasingly large orbitals, whatever that largest one is, the distance between that and the nucleus. So that's the radius of the atom. So atomic size equals atomic radius. Atomic size and atomic radius are essentially the same thing. There's different ways of measuring them, but we don't care about that right now. So if we go across a period from left to right on the periodic table, we see that atomic size decreases. Okay, this is counterintuitive. But what happens is the size of the orbital depends a lot on the quantum number, right? We saw that the 2s orbital was larger than the 1s. And the 3s is also larger than the 2s. When we're going across a period, the principal quantum number of that highest occupied shell is not changing. We go across here from sodium and magnesium, that's principal quantum number 3. We go over here, aluminum through argon, it's all level 3. They're in the same principal energy level, principal shell. So that's not changing. So what's causing the size to change? It has to do with the protons. As we go across a period, the number of protons in the nucleus is increasing, where the distance between the outer electrons in the nucleus is staying roughly the same. But we now have higher charge on the nucleus, and that higher charge is going to pull those electrons in. So that's why as we go across a period, we get more and more protons, and the orbitals are the same size. Because there's more protons, it pulls those electrons in. Does that make sense at all? A little bit? I can't remember the equation, so I won't even go there. As we go down a column in the periodic table, atomic size increases. And this makes sense, because our principal quantum number is increasing. If we go from lithium to sodium, lithium is level 2, and sodium is 3. And potassium is 4, and rubidium is 5, right? So the quantum number is increasing. The principal shell is increasing, and so we would expect that those would be larger. So here's a picture. Pictures are always good. Just showing relative sizes. So as we go down, we see that the elements, the atoms are getting larger. And that trend works out no matter what column we're looking at. That one's usually pretty easy to understand. It's the going across getting smaller that doesn't make sense. Lithium's valence electron is in the 2s orbital. Neon's valence electrons are in the 2s and 2p orbitals, and those are roughly the same distance from the nucleus. But how many protons are in the lithium nucleus? Lithium is element number 3. It's got 3 protons. Neon has 10 protons. 10 protons, we need more pictures. Not a picture like that. That wasn't a good picture. So here we've got lithium. And here we've got, I'm going to make this the same size. Good luck with that. That's not working out at all, because I can't see them. There we go. So 10 plus for neon. So if this is representing the overall size of that second level, the 2s, 2p level, and this is intended to be the same size, it's a little bigger, sorry. These electrons that are out here have charges on them. They're negatively charged, right? The attraction between the negative and the positive charges depends on the distance, and it also depends on the magnitude of the charge. So here we have an attraction of 3 plus, here we have an attraction of 10 plus between this electron and the nucleus. The distance is roughly the same. Because this is attracting more, it's going to pull these electrons in a little bit tighter. Okay, it's a little bit like the force of gravity. Okay, so if you think about gravity and energy of an orbit of a satellite, if the planet has more gravity, it's going to pull those orbiting objects in closer. So because the charge on the nucleus increases as we go across, the electrons get pulled in closer and closer. These trends, you've got right and left, increasing, decreasing, to remember, and up and down, increasing, decreasing. Good luck just trying to flat out memorize that. I think it's much easier to just get this basic concept of why. Going down, that makes sense. They're getting bigger. Okay, we're adding more levels. They're getting bigger. The going across is hard, but these are the same level. Number of protons is increasing, charge is increasing, and they're getting sucked in, pulled in. Enough of that. So, what do you need to know how to do? Something like this. Choose the larger atom in each pair. So, we got to look at the periodic table. So, lead and polonium. Which one's going to be bigger? Lead, right? Because as we go across, more protons, they get sucked in. So it's the lead. How about rubidium and sodium? Which one's bigger? Rubidium. Because as you go down, they're getting bigger.
This example is not our handout.
Oh, sorry. I will repost those slides so that you will have these. I'm sorry. Tin or bismuth? Tin and bismuth. Well, we learned going across and going down. So going across, this bismuth is to the right. That would tell us that the bismuth is smaller, but going down tells us it's bigger. So that's not a nice question, is it? It's not a nice question. So we're going to say we don't have enough information to do that one. How about fluorine and selenium? Here's fluorine and here's selenium. There's another one on the diagonal. But the going across means that fluorine would be smaller. The going down rule says selenium would be bigger. Those two rules reinforce each other, and so we can answer that one. The selenium would be bigger. Okay, and this one we're not going to say we don't have enough information. We'd have to be kind of guessing at that one. Okay, so that's how you apply those trends. Ionization energy. Ionization energy is the energy required to remove an electron from an atom in the gas state. So the electrons are part of an atom, and to pull one off requires some energy. They don't just fall off by themselves. Okay? So the ionization energy also has a trend. It increases as you go across from left to right in a period, because as you go across, those electrons are closer to the nucleus, aren't they? Because the atom's getting smaller. And the closer they are, the more tightly held they are, the harder it is to pull them off. Another way to remember that trend is to think about this. So group 1 elements are on the far left side. If you remove an electron from a group 1A element, you give it a noble gas configuration. Is that going to make it pretty happy? Yeah, it's going to give that electron away pretty cheaply. What if you try to take an electron away from a group 7A element? The group 7A elements have 7 valence electrons. They're trying to gain an electron to get 8. They're going to be really unhappy if you try to take one of the ones that they already have. So that's a higher ionization energy. It takes more energy to pull an electron off. So there's two ways to think about that trend. And the ionization energy decreases as you move down. So as you go down a column, the atoms are getting larger and larger. The force of attraction between the electron and the nucleus depends on the distance between them. So as the distance increases, you might want to plug in your PC. Yeah, I might. As the distance increases, it becomes easier to pull off. And it's not a politically correct example. So, family with one child, family with, 6 children. Which would it be easier to kidnap a child from? The one with 6, right? Because how can you keep track of all of them? So if that helps you, go ahead. So the ionization energy and the atomic size are inversely related. So as atomic size goes down, the ionization energy goes up. Okay, so let's do this example real quick. Choose the element with the higher ionization energy. Magnesium or strontium? Magnesium. It's harder to pull one off of magnesium because it's smaller. Indium or tellurium? Here's tellurium and here's indium. Higher ionization energy. The tellurium. It's closer to the noble gas here. It's also smaller than the indium. How about carbon or phosphorus? Well, we've got opposing trends here, don't we? The carbon should be higher because it's above the phosphorus, but the phosphorus should be higher because it's to the right. And so we're going to say we don't have enough information for that one. How about fluorine and sulfur? Fluorine. Fluorine is smaller, so the fluorine as opposed to the sulfur.